Hi guys, welcome to the lectures of Misostudy. Here today we will be continuing our discussion on properties of definite integrals. In the previous lecture I discussed with you this very fresh 7th property about definite integrals regarding functions which were periodic with fundamental period capital T known to you. So if you have a periodic function with period or fundamental period T, with fundamental period T, then the first thing we understood under this head was that with such a function, when you talk about the very definite integral running from 0 to nt f of x dx, this is equal to n times 0 to t fx dx. I can pull this n out from the upper limit and place it here before the integral only when n is a natural number. Secondly, we also discussed another property which said that from a to a plus capital T fx dx is equal to 0 to t fx dx. I showed you in the form of diagram. A to a plus t was same as 0 to t, the area swiped by the function f. And the third property said that integral nt to nt plus a fx dx is equal to 0 to a fx dx. Whatever is the area covered by the function in the interval nt to nt plus a, exactly same is the area covered by the function from the interval 0 to a. Okay, so computing this integral is same as computing this integral. Similarly, the area swiped by the function f in the interval 0 to t is same as the area swiped by the function f in the interval a to a plus t. Therefore, computing both of them is going to give me the exact same values of the definite integrals, is what is said by these properties. Now, talking about this condition. If I give you this question in which I am saying you have to calculate the definite integral from 0 to 64 pi by 3 and the integrand is 1 plus cos 2x dx. Talking just about the integrand is going to make me reach the step that under root 1 plus cos 2x is 2 cos square x. With this under root sign. This is going to further boil my calculation down to what? Root 2, not cos x but mod cos x. Right? After this, root 2 is going to come outside. I will be left with 0 to 64 pi by 3 mod cos x dx. Talking just about mod cos x, this function is periodic with fundamental period pi. Integrand is periodic with fundamental period pi. I know when the fundamental period is pi of this integrand function, then 0 to nt happens down to be n to 0 to t, n times 0 to t. So over here I have 64 by 3 pi. Can I write it as 64 by 3 multiplied by integral 0 to pi mod cos x dx? Can I take 64 by 3 out of this particular upper limit and put it before the integral sign? No, I cannot do that because 64/3 is not a natural number. Therefore, I cannot write this as 64/3 integral 0 to pi mod cos x dx. This is the wrong step because 64/3 is not a natural number. But when I am talking about 64/3, 64/3 I can write it as 21 pi plus pi by 3. I can write 64 pi by 3 as 21 pi plus pi by 3. That means 21 cycles are being completed by mod x, by mod cos x. Mod cos x from 0 to 64 pi by 3, if it is ranging, that means from 0 to pi, pi to 2 pi, 2 pi to 3 pi and so on, 20 pi to 21 pi. Till 21 pi, there are 21 cycles getting completed. After that, it is travelling for pi by 3 units more. Are you understanding? Till 21, from 0 to 21 pi, the cycles are getting completed. 21 cycles are getting completed by mod cos x. After that, it is travelling pi by 3 more, right? So, till 21 cycles, I am getting a very nice number like 21 pi, where 21 is a natural number. Therefore, this motivates me to break my integral at that moment. And therefore, by using property 3, I will be breaking my integral from that particular point. Here, I will be having root 2 integral. I can write it as 0 to 21 pi plus pi by 3 mod cos x dx. 0 to 21 pi plus pi by 3 is going to have a 21 pi in between. So, this is going to break my interval of integration from 0 to 21 pi plus pi by 3 as 0 to 21 pi and 21 pi to 21 pi plus pi by 3. And therefore, this integral is going to become 0 to 21 pi mod cos x dx plus 21 pi to 21 pi plus pi by 3 mod cos x dx. By property 3, I did that. Now that you have 0 to 21 pi mod cos x dx, now situation is favorable. This is completely resembling the left hand side of the first very point under the 7th property. 0 to nt, where t is the period of fx. Yes, pi is the period of mod cos x and 21 is a natural number. I can pull this out of the integral sign, pull this out of the upper limit. I am going to get 21 0 to pi mod cos x dx plus, here you have 21 pi to 21 pi plus pi by 3 mod cos x dx. This reminds me of the third property, which is nt to nt plus a fx dx is 0 to a fx dx. Here you have the same thing. N is 21, 21 into t is the period, 21 pi to 21 pi plus a is pi by 3 of the function whose period is this t is nothing but 0 to a is pi by 3 mod cos x dx. In the previous questions which we did regarding these properties, we had full-fledgedly computed 0 to pi mod cos x dx, right? It came out to be the number 2. So, you get 21 into 2, which is 42 into root 2. This is root 2, not root 3. 21 into 2, this complete quantity comes out to be equal to 2. So, you get 2 into 21, which is 42, 42 into root 2. So, this is 42 root 2 plus root 2 multiplied by this integral. Now, from 0 to pi by 2, cos function is positive. So, if from 0 to pi by 2 it's positive, pi by 3 is less than pi by 2, definitely from 0 to pi by 3 also it's positive. So, mod cos x is going to just become cos x. There will be no mod sine, it will just be cos x. Okay? Once this has become cos x, I know integration of cos x is nothing but sine x. Apply the limits from 0 to pi by 3. What you obtain is 42 root 2 plus root 2 into sine pi by 3 minus sine 0. You get 42 root 2 plus root 2 multiplied by sine pi by 3 minus sine 0. After this you obtain 42 root 2 plus root 2 into sine pi by 3 is root 3 by 2 minus 0, and that is what gives you 42 root 2 plus root over 3 by 2 as your answer. So that's how you get the answer of such an integral which did not have n pi sitting over here with n as a natural number. No, it did not have that. And therefore, we broke it into some natural number times the period plus some extra element which happened to be called as small a. That extra element played the role of small a, and here as the main element I got n pi or nt type of an expression where n was a natural number. That's how you deal with questions like these, applying these properties. That brings me to an end of properties of definite integrals. This was all about properties of definite integrals. You have to keep a very good track about all of them, because as I showed you, told you, and yes, it's true that they are very, very useful. Understood? Moving to the next topic, which talks about a very interesting situation, which is this. We will be learning about differentiation under integral sign. We will be learning to differentiate under the integral sign. This is the topic we have to deal with. How do we differentiate an expression which is sitting inside the integral sign? I am not talking about d by dx of a function. I am talking about d by dx of integral of a function. Okay? This particular topic deals with three types of differentiations of functions under integral sign. Let's begin the very first one. Three types are there. Let's talk about first the first type. The first type says, here whatever is the rule by which you differentiate functions sitting inside the integral sign, that rule will be called the Newton-Leibniz rule. In the history of JEE exam, there has never ever been a paper without this, without a question based upon Newton-Leibniz rule. Newton's Leibniz rule has to be there in the paper. Even if there is nothing from this chapter, this has to be there. Okay? This is how important this is. So let's begin understanding the rule which is presented to actually tackle with the first type of differentiation under integral sign of functions. What do we have over here? By Newton-Leibniz rule, you learn to differentiate a certain type of function sitting in the integral sign. What are those certain type of functions? Suppose you have integral of phi t dt. Now see, carefully observe, there is a function sitting as the integrand with variable t, t is the independent variable, and the integration is happening with respect to that variable itself. But I am having limits as f1x and f2x. limits are functions of x, and I am interested in differentiating this entire thing with respect to x. So, in the very first type, we are wishing to differentiate inside the integral sign such an expression. Are you understanding? See, try to understand the logic. Here x by which we wish to differentiate, with respect to which we wish to differentiate, is just sitting in the limits, nowhere else. If I am wishing to differentiate with respect to x and x is sitting only in the limits, not in the function, this is what happens to be the first type. The formula of such differentiation becomes what? D by dx of integral phi t dt from f1x to f2x happens to be phi of f2x into d by dx of f2x minus phi of f1x. f1x also is a function of x, so I will be multiplying with differentiation of f1x with respect to x. See what happens. When you integrate phi t with respect to t, you get the answer as a function of t. When you get the answer as function of t, you apply these limits. These are limits over t. So, when after integration you get the answer in terms of t, you apply these limits, your t vanishes, entire expression comes out in terms of x. So, final function which you get after the application of limits is a function in terms of x. When that function in terms of x is there as the answer of this complete definite integral, you will be able to differentiate it with respect to x, right? That is what is being said by this particular type. And how is it computed? Replace t by upper limit, obtain phi of the upper limit multiplied by differentiation of the upper limit minus phi of the lower limit in place of t, phi of lower limit in place of t multiplied by derivative of the lower limit. That is what happens to be my very formula to compute the differentiation of a function inside the integral sign, such that the variable with respect to which I am differentiating is sitting only in the limits, not in the function. Okay? So, if I talk about how did this come actually, let me begin by that approach as well, because sometimes proof gives us a beautiful insight about the very properties which we are studying. So, I am saying phi t is my function. Phi t is my function whose integration I am interested in. So, let integral of this phi t dt, I am over here talking about just one antiderivative, not the entire family of antiderivatives. So, indefinite integral of phi t dt, I am saying, suppose it is gt. Just suppose it is gt. Actually, if I would have been writing, it would have been indefinite integral of phi t dt. This is dt. Indefinite integral of phi t dt is gt plus c, the constant of integration, but I am not writing it. I am interested in definite integration. I just want one antiderivative. So, suppose this is that one antiderivative. If gt is one antiderivative, this implies d by dt of gt is phi t. Until and unless differentiation of gt is not phi t, I cannot declare gt to be a primitive of phi t. So, if gt is an antiderivative or a primitive of phi t, that means differentiation of gt is phi t, right? This implies g dash t is phi t. Nice. So, now over here, after you have got this, then what you do? Integral phi t dt. See, first of all, step by step movement. First of all, you compute this integral, indefinite integral. After that, you apply the limits over t. This becomes t equals f1x is the lower limit, f2x is the upper limit. One antiderivative you have obtained, and then how do we write it as? f1x, f2x, which is standing for what? G of f2x minus g of f1x, that's how we do definite integrals. After this, the next step is to take d by dx. See, on the right hand side, the entire expression is in terms of x. It is valid to talk about d by dx. Then d by dx of the left hand side, which is this. First it was phi t, then integral phi t, one antiderivative, then with the limits, then with the differentiation sign. This is equal to d by dx of g of f2x minus g of f1x. Next step. G of f2x minus g of f1x. This is d by dx of g of f2x. What is the differentiation of composition of functions? It is g dash f2x into f2 dash x minus g of g dash f1x into f1 dash x, right? Which is what? G dash f2x, that is, if I talk about g dash f2x, what is g dash? What is g dash? G dash of f2x. I know g dash is phi. So g dash of f2x will be phi of f2x. This will be phi of f2x into d by dx of f2x, which is f2 dash x, minus, again g dash is phi, so phi of f1x into f1 dash x means d by dx of f1x, and you obtain your result, which is nothing but equal to. So you know what basically I want to point out to you is, by this proof, that either first you calculate the integral phi t dt, get a function in terms of t, then apply the limits, because limits are in terms of x, the answer is now going to be in terms of x, t will be eradicated. Once you have got the limits in terms of x, you have applied and you have got the final answer in terms of x. After that, differentiate. Either you work like this, or you directly replace t by the upper limit multiplied by the derivative of upper limit, minus then phi of replace t by the lower limit multiplied by derivative of the lower limit. Both these are going to give you the same thing, a very beautiful formula. This is known as the Newton-Leibniz formula or the Newton-Leibniz rule. Beautifully applicable and thoroughly asked in exams. Very, very, very much asked in the exams. As I told you, this is Newton-Leibniz formula. Okay? Talking about the applications of it, how would that be understood? If I talk about the applications of it, the Newton-Leibniz rule or the Newton-Leibniz formula, okay. So I am giving you this says 0 to x ft dt is equal to x plus x to 1 t ft dt. Let 0 to x ft dt is equals to x plus x to 1 t ft dt. Then find f of 1. First of all, you have to find f, then only you can find f of 1, right? How do you find f? Just try to look at the statement of Leibniz rule. It is saying phi of f2x. First of all, integrand has to be a function independent of x. X is that variable with which you are wanting to differentiate. Over here also, my integrand is a function of t, not a function of x, which is sitting in the limits, right? So x is sitting in the limits only, not sitting in the integrand, and with respect to x I am wishing to differentiate. Same is the scenario with me here, same is the scenario with me here. Function, the integrand is free from x and x is sitting in the limits, okay? Over here, it talks about if you differentiate it, it talks about phi of f2x. Somehow if I differentiate, suppose I differentiate, I will get f of upper limit, which is f of x. I want that. So somehow this is signaling me, even over here if you see, f of lower limit is going to give me again xf of x. So somehow this is signaling me to differentiate both sides and see if I am getting function of x or not, because here it is asking me to calculate f of 1. For that I want f of x. So what I'll do is differentiate both sides with respect to x. Differentiate both sides with respect to x. You get d by dx of integral from 0 to x ft dt is equal to d by dx of the sum is sum of d by dx. So d by dx of x plus d by dx of integral from x to 1 tft dt, right? What is d by dx of this integral expression? This is of the first type, where the integrand is free from the variable with respect to which differentiation is happening, and that variable is sitting only in the limits. So by Newton-Leibniz rule, I get this is f of the upper limit into d by dx of the upper limit, which is 1, d by dx of x is 1, minus f of the lower limit into d by dx of 0, which is 0. That's my left hand side, equal to d by dx of x is 1 plus what is d by dx of now this integral? Again, this is of the first type, integrand is free from x and you are differentiating with respect to x only, which is sitting only in the limits. Therefore, over here I am going to again apply my Newton-Leibniz rule. This says integrand, substitute in place of integrand wherever you see t by upper limit. So this will be 1 into f of 1 multiplied by d by dx of 1, which is 0, minus x into f of x, lower limit, x into f of x multiplied by d by dx of lower limit, which is 1. Right? What you get is fx, 0 into f of 0 is 0. You just get fx. See, that's what we wanted. On the right hand side, you get 1 plus f of 1 minus, what do you get? This is 1 into f of 1 multiplied by 0. So this term completely becomes 0, minus x into fx. So 1 minus x into fx, right? So you get fx plus xfx, fx plus xfx equals 1. Take out fx common, what you obtain is when you take out fx common from here, you get fx 1 plus x equals 1, right? So this becomes fx is 1 upon 1 plus x. If fx is 1 upon 1 plus x, therefore f of 1 is 1 upon 1 plus 1, which is 1 upon 2. That's your answer. That's how you obtain f of 1 once you have f of x, by the application of 2 times we applied left hand side and right hand side the Newton-Leibniz rule. Understood? This is one way in which many a times JEE has asked questions. That is, you have to yourself understand that I will have to differentiate both sides in order to get what I want. The other thing which can come in the Newton-Leibniz rule is of this kind. Limit x approaches pi by 2, integral of 1 to x 2t dt, or let me write fx, x approaches 1, not pi by 2, x approaches 1 upon x minus 1, right? Over here, if you try to substitute 1 in place of x, denominator becomes 0, numerator becomes 1 to 1 2t dt. 1 to 1 integration is 0, so you get 0 by 0 form. 0 by 0 form, applying what? Applying L'Hopital rule. L'Hopital rules, what does it say? This limit is equal to the limit which you obtain when you differentiate numerator and differentiate denominator with respect to x. So, this will be d by dx of integration from 1 to x 2t dt whole upon d by dx of x minus 1. In the numerator, I wish to differentiate the term inside the integral, where the integrand is free from x and x is only in the limits. Clear signal is to apply the Newton-Leibniz rule. This will be equal to limit x approaching to 1. What will be this? Twice of upper limit. Just replace t by upper limit. Replace this t by upper limit multiplied by differentiation of the upper limit with respect to x minus twice of lower limit into differentiation of the lower limit, which is 0, whole upon d by dx of x is 1 and d by dx of 1 is 0, so you get just a 1. Over here what you have obtained is limit x approaches to 1 2x. Clearly this is a continuous function and limit x tends to a, fx, where f is continuous at a, is f of a. So 2 into 1 is your limit. That's the answer. So that's how, in terms of limits also, when you have to differentiate numerator and denominator, the numerator can be given in this form, so that when you apply L'Hopital, the numerator after differentiation demands the use of Newton-Leibniz rule. Okay, deliberately they construct such as the numerator. It is pretty easy. Over here direct integral also is very easy, t square by 2. But if you apply this Leibniz rule, that's how the situation becomes and you get your answer as 2. This is the case which takes place when you have the first very type of differentiation under the integral sign. If I talk about the second type now, so first type was what? I was differentiating with respect to x and that x was sitting just in the limits, not in the integrand. The second type says I am interested in differentiating with respect to x, but this time x is not sitting in the limits, limits are just constants, but x is sitting in the integrand. So, second type is what? The formula to compute differentiation with respect to x of the function sitting inside the integral which has x and t both, and the limits are just constants a and b. So x with which you wish to differentiate is sitting in the integrand along with the independent variable with which the integration is taking place, but not in the limits. Here it was just sitting in the limits, not in the integrand. That's how types are differentiated. This is equal to integral a to b del by del x of phi of xt dt. Now what is this? Basically, try to understand step by step. Phi of x comma t is a function of x and t. When you are going to integrate it with respect to t, I am talking about indefinite integration. When you are going to, irrespective of the limit application, when you are going to integrate phi of x comma t with respect to t, you are going to get the answer in terms of x and t. When you get the answer in terms of x and t, once you apply the limits in place of t, these are constants, these constants come into picture and t vanishes, but x still remains. So after the application of limits, the entire function which remains is in terms of x. Understood? This complete integral after the application of limits is remaining in terms of x, so you are completely differentiating with respect to x, which makes sense. Over here if I come, till now you have understood that t and x are, t is just not dependent upon x, t is vanishing by application of limits, only x is remaining. So t is just not responding to what x is doing. Therefore, over here what we do, what comes out, this comes out to be equal to what? That what you do, you partially differentiate this function with respect to x. That means partially differentiate means phi x comma t is a function of x and t. Treat t as constant. T will be treated as constant. Only differentiation will be taking place with respect to x. Wherever t is there, treat it as constant. Keep treating it as constant. Only differentiate the function phi xt with respect to x. When you do that, you basically are just differentiating the x portion of this phi xt function by taking t constant. What remains is the differentiated function now phi xt with respect to x, t constant. Then you integrate it. Again you are going to get function with respect to x and t. Plug in the limits in place of t, t vanishes, again you are left with function of x. So either you differentiate the function first with respect to x keeping t constant, then apply the limits, or in the end after integration, after application of limits, you differentiate with respect to x. See, over here I am not talking about partial differentiation, because when the limits are applied, t vanishes. Only what remains is expression of x. So here, if I only have x in my function, why will I partially differentiate with respect to x? I will have to completely differentiate only with respect to x, keeping nothing as constant. No variable I have to treat as constant. But over here when I am differentiating, t and x both are acting as variables. So I have to keep t as constant right now and differentiate with respect to x. Both these are going to give you the exact same result. So whenever you have this type of an expression where you wish to differentiate with respect to x, term inside the integral where x is sitting in the function, not in the limits, this is how it is treated. Okay? Moving on to the third type. There is a third type as well. As I told you, there are three types. Third type is when x with respect to which you wish to differentiate is sitting both in the limits and in the integrand. In the first case, it was sitting in limits, not in the integrand. Integrand was free from x. Here, x was sitting in the integrand, not in the limits. Limits were free from x. Here, I will be interested in differentiating such a function in which I have integrand also having x and limits also having x. In this case, both first and second type are going to come into picture. See beautifully how first and second results are combined to give the result of this third type. Here, what I did, keep in mind, phi of upper limit into derivative of upper limit minus phi of lower limit into derivative of lower limit. This I did, and what I did over here, I partially differentiated the function which had x in it with respect to x, and then I am integrating. So over here we do the same thing, combine the first and the second result. You get phi of x comma, in place of t, substitute f2x multiplied by f2 dash x. There also we substituted t by the upper limit, here also substitute t by the upper limit, minus phi of x comma, substitute t by the lower limit, into f1 dash x. Exactly same thing which we did in the first type. Then what you do is plus integral f1x to f2x del by del x of phi of x comma t dt, what we did in the second type. And this happens to be the formula to compute such differentiation of functions inside the integral sign. This was all about the three types of differentiations inside or under the integral sign. One thing which I just want you to notice, when I am talking about such functions having both x and t, x over here can sit as explicit or implicit variable. What I am trying to say is, if you have 0 to 1 x sine t dt, this is also the integrand which has x and t both, but x is sitting explicitly, I can pull it out, so you are allowed to do it like this, because these limits are limits of t, not limits of x. So these limits are not of x, you can take it out. But if you have x sitting implicitly, like sine of x into t dt, still the limits are of t, but now you cannot pull x out. So this x can either sit implicitly or explicitly. Depending upon it is sitting explicitly or implicitly, you can even take it out to solve your questions, or you may not take it out as well. Here both these types of functions in which x is sitting implicitly or explicitly is dealt in the same manner. This formula is true for functions phi xt with x sitting implicitly also and explicitly also. Similar is the case for this. Okay? Keep these formulas very, very nicely in your head. They are very useful and important from examination point of view. Thank you. That's it from my side.